Καλησπέρα. Ξεκινήσουμε. Μελά κύριε Μπαρδακή. Εκ μέρους των εταίρων του προγράμματος SAFE και της
the partners of this program, SAFE, Alpha and Associates, I would like to welcome you to this event. The purpose of this event and the ones that will follow is to show the need for a combined structural and energy upgrading of buildings. We have dozens of designers in Europe who have studied and proposed solutions. The question we have to answer today is whether we will act timely or whether we will keep on talking about this topic, especially in Greece, which is a country with a very high seismic hazard. Now, Mr. Thanasis Kontogiorgis, Deputy Minister to the Prime Minister, has an impediment and won't be able to join us, but he has sent a short address. The recent destruction has shown the urgent need to upgrade buildings and infrastructure in order to deal effectively with the climate crisis and natural phenomena such as earthquakes. It's important to put emphasis on combined actions that will protect our environmental footprint. These actions will allow us to do more with less. I apologize for not being with you today. I wish you good luck with your event, in which well-acclaimed members of the scientific community participate and which is supported by the EU program Horizon. Now, Mr. Stasinos, who is from the Technical Chamber of Greece, has the floor. Good afternoon. I would like to congratulate all those participating in this program, all those making this effort, because we are living in times which are difficult. It's not in theory anymore. We see the signs, the problems caused by climate change, and we understand how quickly we have to adapt, how quickly we have to change the infrastructure in order to respond to the needs. 10 or 15 years ago, we were discussing about the consequences of these phenomena in the future, and it seemed something very distant. But now we've had the recent events, the floods, the wildfires. As a professor of mine used to say, every day a big earthquake is closer. So it's not only that. There are also financial reasons that dictate prevention. It has to become our priority. I usually give simple examples to explain that. It's better to repair 5 cracks when it's early than to repair the whole building when it's too late. So we have to be more pragmatic. We should not stay with the theory. We have to make our buildings more resistant. And with the Recovery and Resilience Fund, we have this opportunity. And until recently, nobody would pay attention to the term resilience. We would only speak of recovery. We would say recovery fund and stop there. But resilience is even more important. And you understand that in order to reinforce buildings, we cannot drive people away. We cannot tear them down and build them from scratch. In other words, we need optimum solutions to be able to reinforce our building stock as quickly as possible, in the most satisfactory way possible, in the most scientific way possible. Especially here in Greece, where earthquakes were a dominant problem, now we have other issues as well. And we have the issue of energy savings. With these words, I would like to tell everybody who makes an effort in this field, me from the technical chamber and all my colleagues, to try to make things better with better techniques and every effort possible.
Καλησπέρα από μένα. Θα ήθελα και εγώ με τη σειρά μου να σας καλωσορίσω στην εκδήλωση που διοργανώνει η Σάλφο στο πλαίσιο του προγράμματος e-Safe και να σας ευχαριστήσω εκ μέρους όλων μας για την παρουσία σας σήμερα. Θα προχωρήσουμε τώρα στο πρόγραμμα της ημέρας.
So we're going to continue today with the agenda with Mr. Vardakis' address, and he's the president of the Association of Civil Engineers.
Αγαπητές οικοδέσποινες και αγαπητοί οικοδεσπότες, φίλε πρόεδρε του ΤΕΛΕ, αγαπητές και αγαπητοί συνάδελφοι,
dear colleagues, I'm very pleased to be here with you and to participate in these opening addresses. I have both personal reasons and professional reasons to be pleased. Let me tell you about the personal reasons. I must say that I'm very scientifically minded and I like to look at the structural studies in depth. And I work in Patras, and there Mr. Triadafilou has his laboratory, and he's trying to ensure that we have energy upgrade as well as structural renovation. And I would like to say that the Technical Chamber of Greece had said from the outset, when we had the directives for energy upgrading, we would find results that are unreasonable. If we have to upgrade a building that does not have the necessary structural adequacy, then we will have to remove the energy upgrades and take things from scratch in the right order. I don't want to tire you because there's a afterwards, but this is true in all the areas that tend to have earthquakes. I have, in fact, Samos as an example. We had, in fact, made certain energy retrofitting, but after the earthquake we had to remove them in order to have structural renovation first. So I think it's very important to take things in order or to have simpler solutions. But we all know that there are quite a lot of things that are difficult, such as how we are able to transfer the forces, and you know how it is very difficult to have the foundation of the circumferential connectors that would take part of the tension. So these are problems, but they are not the reasons why we would stop. No, far from. They make us buckle down and study it more closely, because that means that we'll find the best solutions. This will be something that will help society and citizens. I will end my address here. Thank you very much. I hope that this will be a very successful event. Terribly sorry, couldn't be heard.
Καλησπέρα, κύριε Μπουρνά, μας ακούτε? Γεια σας, καλησπέρα. Εμείς είμαστε έτοιμοι, αν θέλετε να δοκιμάσετε να δούμε.
We're ready. Can we see whether you can hear us? And we can hear you?
Δυστυχώς δεν σας ακούμε.
Unfortunately, we can't hear you. Can we just check your sound?
Πριν λειτουργούσε.
Ωραία, είμαστε εντάξει.
It was working before. We can hear you now, yes.
Με ακούτε μια στιγμή να συνδέσω ακουστικά, μήπως.
If you can bear with me 1 minute, I'll put my earphones on. So Mr. Bournas is from the Joint Research Centre in Brussels, and he is speaking via Skype.
Τώρα πώς με ακούτε?
Can you hear me now? Yes, we do. But there has been an additional screen on your slides. Okay, it's
Ωραία,
been
ήταν
now. Yes.
Το Teams. Οπότε τώρα και με ακούτε και με βλέπετε, μπορώ να ξεκινήσω?
So you can see me and you can hear me, so I will kick off. Yes, please do.
Καταρχήν, καλησπέρα σας.
So good evening.
Θα κάνω την παρουσίαση στα αγγλικά.
I'm going to make the presentation in English, obviously.
Thank you for this invitation to present some of the activity we have been doing at the Joint Research Centre of the European Commission on this topic of integrated seismic and energy renovation of the existing buildings. My name is Dionysios Bournas and I'm Scientific Officer and Team Leader at the JRC. There's a delay. Yes. First of all, the JRC, to put you in context, is the Science for Policy Service of the Commission. And we provide independent evidence-based knowledge for the EU policies. We have our headquarters in Brussels, but we are divided in 5 sites, with the biggest being in Ispra, where I'm also based. Now, regarding this talk, it includes 4 areas about buildings and EU policies. I will start, then experimental assessment activities for existing buildings, then novel technologies for integrated retrofitting, and I will close with the evaluation of the integrated retrofitting. So, the main issue in Europe is that our buildings are old. They are quite energy inefficient. 75% of our buildings are energy inefficient, consuming the big majority of the total EU energy, 40%, and generating 36% CO2 emissions. On the top of that, 1/3 of Europeans are exposed to earthquakes. So when we are speaking about renovations, we should take into consideration the seismic together with energy. Now, in terms of EU policies and initiatives, we have the Renovation Wave initiative. Today, we renovate around 1% of our buildings. That was the figure in 2020, but we need to do more to reach 3% if possible. That was even highlighted last year, let's say, with the crisis of energy and the need to reduce the dependence on the Russian gas. So energy renovation is a key element. However, if we see the Energy Performance of Buildings Directive itself, it states that countries need to use their long-term renovation strategies to address also seismic and risks and fire safety. On the top of that, the recovery and resilience plans following the pandemic found many countries to propose integrated renovation schemes. So, in this presentation, I will start with the experimental assessment of existing buildings. We did that by designing and constructing a full-scale prototype building, typical of the pre-70s construction. This is the masonry infill RC frame, and that was done at the European Laboratory for Structural Assessment. This is the ELSA lab in Ispra. Here you can see a video where this building was transported into our laboratory. I don't know, do you see the video already?
No, we can see. Oh, yes, it's moving, so it's a video.
There is a delay. This is to give you an idea of the scale. This is the full-scale prototype, and we did seismic assessment tests, but also tests to evaluate the energy efficiency of this building. So in a series of tests, we initially evaluated what is the energy efficiency by means of blower door tests, and then we conducted earthquakes. We saw that even a slight damage, as you can see here, could reduce the energy efficiency significantly. Even a slight damage that we wouldn't consider for strengthening, because it's only minor. And then we continue until bigger earthquakes, and yeah, I will go directly to the next slide, where it shows the last test at a peak ground acceleration of 0.30 G. This corresponds to a design level earthquake, both in Italy and Greece, I would say. And in these two videos, you can see that the masonry infill is completely destroyed. Those damages that were noticed are not repairable. So the outcome is that under stroke earthquake, we have damage that is not easy to fix because of the high costs. But even in small earthquakes, we saw that the thermal performance of the building is reduced. So if you are with me in the same slide, now this is the response of the building we tested. Just to show you in the last figure, at the 0.3 peak ground acceleration, we had a reduction of the strength of the building of 30% due to the damage of the infill, of the masonry infill. Yeah, you can find more details about this study in this recent publication, which is open access, and we could provide to you. The next step now, since we saw the vulnerability, is to apply novel technologies for integrated retrofitting. In this slide, there is a categorization of integrated renovation technologies. I would say that someone could do integrated exoskeleton solutions, but this is a quite expensive solution. Interventions on the envelope of the building, which appears to be cost effective, or intervention on horizontal elements. We focus our work on this type of interventions. As following an analysis we did, we saw that both in terms of costs, but also in terms of effectiveness, these two methods could be very effective. This state-of-the-art review provides more information on analysis of technologies that someone can use for integrated retrofitting. The first step was to use timber, bio-based materials. This is a project Notice EUB. This is a Marie Curie fellowship we hosted at the JRC. And now we went to the previous building. We demolished the damaged infills. Are you in the same slide with me? Yes. Okay. So we replaced the damaged infills and we installed cross-laminated timber panels with two different configurations. In the first floor, we installed timber beams, which were fixed to the beams, and then on the beams we fixed the CLT panels. And at the end, thermal insulation inside. In the second floor, the CLT panels were installed directly to the concrete beams, as you can see here. This would allow to install the strengthening scheme without removing the infills in case of existing structures. The next video, it takes some time. Here we have the video where the same specimen was tested in much larger earthquake, 0.45 G. I hope now you can see this video. Did you?
Yes, before we could, but now the slide only is about science policy of the John Center.
Okay, that's the end of the video. And then there is another video that in which you can see the connections at the beam column joint and the rocking of the panels. Overall, this technology proved to be very effective and damage-free up to a very large earthquake. Another system that we also tested was the use of advanced materials with thermal insulation. That was also tested by other researchers for masonry structures. We here tested this for reinforced concrete buildings with masonry infills. The idea here is to first provide seismic retrofitting by strengthening the masonry and then add also thermal insulation. I will go directly to the a bit faster to the slide which shows the retrofitting. So in the same building we rebuilt the infills. We did retrofit the joints that were cracked because of the previous test, and after that we applied this material here, which is called textile reinforced mortar. So we have basalt fibers, jacketing with mortar around the infills, as you can see. And at the end, on the top of that, we have external thermal insulation. This is the building at the end of the application. And this is the last video of this campaign where we tested 2 large earthquakes until damage of the building. it survived very large earthquakes without damage, and then we went ahead with doing cyclic tests until we had the failure of the system. Did this video finish? Okay. So overall, we saw that an retrofitted full-scale building at the design level earthquake of 0.30 G leads to big damage and collapse of the infills. The CLRT retrofitted survived an earthquake which is 50% higher without significant damage. And the TRM retrofitted with thermal insulation also, it was quite elastic until PGF 0.35 G, but then had a drop of 15% at the maximum earthquake. Besides, at the same time, we have had the international collaboration with the Korean Construction Engineering and Development Collaboratory Management Institute, KOSID, where we developed a novel prefabricated textile reinforced concrete panel with integrated capillary tubes. You can better see this concept here. This is a lightweight prefabricated concrete panel that can be applied very quickly and very economically on site. Of course, in our case, we developed and constructed it in small scale in a lab. So we can have here the reinforcement with the capillary tubes, the mortar, and this is the finishing to connect the circulation ensure the circulation of the fluid. This is like floor heating, but is applied now to the envelopes, and we did test this system for retrofitting of a full scale of a hull scale frame with infills. We show that it's very effective in increasing the strength, but also it can stay in place at very large drifts without significant damage or very high degradation of the strength. At the end, we did also thermal performance evaluation, specifically in a case study of a residential building in Korea, in Busan. Those panels were installed inside or outside the building, and the objective was to keep the temperature of this building to 20 degrees. That was achieved in the winter time, of course, and we also studied two different temperatures of the fluid, 25 or 50 degrees, and we saw that even 25 degrees were enough for this system. And on the top of that, 25 degrees can be achieved by using of photovoltaic panels, as opposed to 50 degrees of Celsius where the activation of boiler was necessary. So overall, this system was proved to be very effective both for seismic and energy features, and more details can be found in this publication. Let me go also to two tests we did in collaboration with our Korean colleagues in Busan National University. Here, that is a scaled building in comparison with the one we did at the JRC. It's also have less openings, but we show here that this is the under-retrofitted building. We have in-plane damage, and after that, out-of-plane collapse, because this is a real earthquake with two directions of loading. And we had collapse of the infills in the second floor. Whereas the TCP retrofitted specimen survived a very large earthquake which corresponds to the 200% of the design-based earthquake. Here we exceeded the capacity of the shaking table, so we stopped and had only some damages, as you can see here, which were repairable. So these systems were very effective, and we have conducted very quickly. I will go now to the impact evaluation of these systems. We did consider the European building stock in terms of the building's age, material, and height. We consider different locations, and we conducted building energy modeling, around 1,000 analysis on different building typologies, plus seismic fragility analysis, and all of these were translated into costs at the end. What is the expected annual loss for non-retrofitted and retrofitted buildings, and all of these, what could be the benefits of retrofitting. So we could assess whether the investment is cost effective. For doing this analysis, we selected 20 European cities with different climatic conditions and seismic hazard levels. As you can see in this map, I'm not going to go into detail into this, but just to keep that we have diversity of those conditions. What is important to know that both the seismic and energy standards were absent before the 60s. So if you see before the 60s, in most of the European countries, there is no seismic design, and the thermal resistance is very low. So we prioritize our renovation scenarios for those buildings, and of course, for those from 60s to the 70s. Two messages from this work is that if we increase the renovation rates by from 1% to 3%, we can have up to 32% reduction in energy use and 38% less CO2 emissions by 2030 already. Note that these numbers relate to the energy and emissions from buildings only. But most importantly, for seismic regions, we can reduce the payback period of the retrofitting investment significantly for high seismicity areas. Again, more information can be found in this paper. So to close, seismic and energy retrofitting is required in seismic areas of the world, and this affects a large part of our building stock. Specifically for pre-70s masonry infill concrete structures, there is problem with the infills, and this was proved to be catastrophic. I mean, the damage were proved to be unrepairable at 0.30 G. The novel cross-laminated timber panels investigated were found to be very effective until we stopped the testing, 0.45 G, but still the system remained practically undamaged. Both the TRM jacket plus thermal insulation and the prefabricated panels with capillary tubes could enhance both the seismic and energy retrofitting at very high standards levels. We saw that in Europe there will be a huge improvement of the energy savings and reduction of CO2 emissions if we increase the renovation rates, and that it's clearly a good idea to implement integrated retrofitting for areas with high seismicity. So this could further incentivize the renovation rates. So thank you very much for your attention. I'm sorry for the delay in coming from this presentation. I have here put some references for you, but feel free to contact me if you need any more information. closing, I would like to thank a big number of collaborators that we have worked over the last 5 years on this topic, and this research is part of several projects. So thank you for your attention.
You can stay with us until the end, because we will have some question and answers. The next presentation by Mr. Vardakis from the Union of Civil Engineers of Greece.
Είπαμε με τον Άγγελο να έχουμε ποικιλία.
Angelos and I decided to have a variety of languages in this event. So you will hear Greek, but you will look at the presentation in English. We have several examples in our country. If you take into consideration that the regulation for concrete buildings started in 1974. Before that, we had some sporadic, let's say, efforts at the Agios Andreas Hospital and some important buildings that had been affected by the earthquakes. Now, 13 years after this regulation, we have many examples of concrete interventions and other technical works. And, of course, we can have some tables with the financial results and show which interventions are more costly than others. We will present that in conferences, etc. There is a certain gap, let's say, room for improvement as regards buildings and their masonry. We have the code 2018 and the draft that will come after that, which is about masonry. You see some examples from Samos. This is the primary school in Anovathi. There are some buildings that were upgraded from an energy point of view. The first priority is to avoid having victims, but then after that we have some issues with the management of a project when the administration and the municipality have not had the time to support, to reinforce the buildings. And in Samos, a great number of schools were non-operational anymore. And many other things, but let's stay with buildings because this is today's shopping. This is in Anovathi, the primary school. We had part 3 of Eurocode. We had to document for the real resistance of the materials. Many of these buildings were listed and are listed, so we have this procedure by the Ministry of Culture, which has certain preconditions. Then we have this construction, a technique they had in Samos before those intervention regulations. They had their own technique. Whenever there was a crack or a pathology, they would put these elements concrete frame, let's say. This is the floor plan of the building. In the past, in 2000, at an irrelevant point in time, they had these concrete frames. They reinforced the building, not because there was an earthquake. And then some others are intact. On the right, they have another intervention. They wanted to create an amphitheater. And they removed a pillar. Look at the pathology. If you go back, you will see that the left part is the one where we had this strange intervention. It's different from the other part. Then, of course, we had more advanced technologies used, 3D tomography and georadar. Here you can see the interventions that had to be calculated in order to go up to level B1. This were enough to go to this level because usually in schools and other similar buildings, this is the minimum goal. Now, by consent of the owner, we can go lower. This is something that the regulation allows, but for these public buildings, this is the lower limit. A design that was optimized, but we have to have many interventions. We had to use TRM, and for rigidity, we had to intervene where the pillar was removed. Here, we had a quick on-site control because the first who visited the place actually thought that there would be no problem, but after the plaster was removed, it seemed we saw that the masonry was problematic. There were many cracks. We had to use a belt, which is usually used to lift loads, to wrap it around the building to keep it in place, to avoid deformation. Once again, an intervention to avoid deformation. This is the gym of the high school, first and second high school. All interventions were removed, it was reinforced, and it was renovated. There was an energy renovation. That's a waste of money, and the investment was pointless here. Once again, we could not cover B1 this target, the B1 level. We had to use once again the same technique. Now, if we take into consideration all the buildings, what we did was to have repointing mortar joints. These were very listed buildings, as I said before. For TRM, we had to use a matrix which is compatible with the material in the masonry, because in most buildings we didn't have concrete. So the TRM material, the mortar, etc., should not be like that. Then FRPs, steel beams and compression struts, and of course the masonry that was repaired in the way I described before. Here, another picture from Crete, an administrative building, and then a school in Heraklion. Here we have a structural model for non-linear shell elements. There was a model for the envelope, once again non-linear. We saw the quarter deformation, the arc deformation, the quarter deformation, sorry. And here, pushover. Here you can see the methods that we use for concrete buildings, FRP wrapping, joint strengthening, infill isolation, addition of steel frames and bracing systems when we have to create resistance and rigidity. And once again, concrete buildings in Heraklion. The university had these buildings. Once again, performance-based intervention. We had to do mass reduction in order to achieve the target. We had to remove a slab and use timber instead. Then we had staircase isolation. And I think I used my time as I should. So thank you very much. We would like to thank you too. Now, Mr. Mandopoulos. Mr. Ladopoulos from Hellas CO. We cannot hear the lady when she speaks. She's off the mic.
Καλησπέρα σας. Ευχαριστώ πάρα πολύ για την πρόσκληση.
Thank you very much for the invitation. Let's just talk about the environment that we find ourselves in. It was a major crisis, and once the crisis ended, then COVID came. But we did not give up. And when we started getting back on track and being a bit more optimistic, we had the energy crisis. And we said that that would be the worst. And then we had the war. I think that even the best manager, and we have quite a lot of these today, it would have been impossible to find all the threats with the best of SWOT analysis in order to know how to solve things. Nevertheless, we have even greater problems and things that we considered to be impossible, or something that would only happen far from home, in Australia or the States or Saudi Arabia, happened. And they said, well, this is temporary. But we see that they happen more often and more extreme. And they are here to stay. These are the targets, and we have to achieve them. I think we know them off by heart, both in terms of energy and in terms of emissions. This is a huge problem. How will we solve it? the solution is to think out of the box. Let us try to do things that must be done. We can't leave it by the wayside. This has to be done. This is a project in Paris and this is a greenhouse and crops on a rooftop where we see that all the energy for the greenhouse happens from or is provided by a data center in the ground floor. This is rather specific and rather special, but I'm showing this to you because it's not only CapEx, well, this was expensive, but it's OpEx also, what we want to gain and where we want to go. So energy upgrading, as it's happening not only in Greece but elsewhere also, it's as if we're applying makeup when open heart surgery is really required. Until now, energy upgrades in Greece took place without taking into account the passive fire protection of a house and without structurally reinforcing it. And we know that energy upgrades meant actually lighting, insulation, openings, a bit of BMS, a bit of cooling, in the best of cases. These are the programs that have been running in Greece with energy savings programs and the Electro program, an energy upgrading program for public buildings, and the net metering, which will become net billing, and e-mobility. In red, you see the association has proposed. It's an energy savings plus with respect to major companies that have a large building stock. So the footprint of their energy upgrading would be much larger. And these are the various letters that we've sent. But why am I talking about this? Because I would like to note that in Taipei, the privatization fund, that is, when there were various movements made in this direction, they took these points into account and they looked at the structural adequacy. So this was a step in the right direction. So let's talk about the good side of these things also. Now, what must be done? We have to act holistically. We must not act independently in order to avoid what Mr. Bardakis referred to, whereby we have to go and remove the insulation or other materials that we'd placed before, and money goes down the drain. Now, Kinak, a new Kinak, this is very important because on that basis, a lot of projects are going to be constructed, and we have to see whether this has further problems and additional cost. We want to have real energy upgrades and not to simply have procurement tenders, innovative technologies. Let's take into account user needs also, take on board digital transformation to make certain that the tenders should take place fast. Tenders delay, even though there is the intention on behalf of the state or otherwise, they are still delayed. And that means we might well lose funds from the various funds. And you know, the design officers should not also have to do everything at once. specifications for materials, and design according to budget. So those were a few of the points that we already include, and this is a step further in our projects. And these, in fact, can be lead beam, KNX DALI, constant light control, energy monitoring. We have water fixtures for low consumption, ASHRA incorporation, and electromobility load control. This is very important. It's something that we will have to deal with in the future because we really need to enhance the power transmission system. We also have rainwater management. I would like to talk about that later. Net metering and all those systems that we use in the various projects that we are working on. These are prerequisites. Now, what's the step further? Based on standards that not only look at sustainable but also keep in mind the well-being of users, we have the circadian lighting, human-centric lighting, and we want to have the moisture management, and after COVID, we need to have very special filters to have a good air quality. I would like to show two projects because these are things that are not in our imagination and they are being realized in the private sector. This is the Eleftherotypia building. It's something that we have done for demand, and all those points that I raised before were incorporated. And these are photographs from render and one from the implementation. When I prepared the slide, I couldn't remember which was which, which is a good thing. And this is the Prodea office, and this underwent a well certification. Here you see that we had listed building facades, and very beautiful building, but in order to be implemented it needs money. But in terms of energy, the cost for the two buildings was not high. So the investments might have been quite high, and the architectural side might have been expensive, but the energy side was not that expensive. Is NZEB a solution? I would opt for a positive energy building, but that is also a trap because we see that the energy design takes place, and because through a PV we can achieve the class that we want, we end there and we don't take it further in order to ensure the true energy upgrading of the building. I think that's the most important problem. How will we incorporate in the energy upgrading of the program and in the regulations of the GNAC the issue of climate change and the EU directive? And I would like to say that I was in the working steering committee that Rambo prepared, and this has already been handed to the General Secretary, trying to incorporate some of these elements in the new regulation. Digital transformation, I think that we cannot do anything without it. So if we can imagine buildings that will not have IoTs, into artificial intelligence, which will be connected in a cloud, these appear to be remote or far-fetched, but they are being delivered, even in Greece. We have tools. BEAM is one such. It can help. It can help in reducing cost, in reducing time, hence cost. I don't know if we are ready yet to work in 8 or 9D, but in certain projects we go up to 60, even at Ellinikon. We can use this as a tool and not as a 3D design. we have to understand that we can no longer talk about 3 dimensions. This is a tool that takes us further. This is an SOM project where they want to use, it's a concept, where they want to use the buildings in a city to filter the air and to return it pure outside. But we have to think a bit more. Money is a problem, that's obvious. This is not an easy thing. But we saw the consequences. We saw where we're at. And it's time to act. I think it's high time to do so. Thank you.
Thank you very much. The next presentation is by Mr. Giuseppe Margani from the University of Catania, Introduction to the EU Project is Safe.
So, thank you very much, Aphrodite. It's a great pleasure, also a big honor to be here in Athens, one of my favorite cities in the world, I must admit, really nice. And I mean, I come from Sicily, so our roots are in common. We have been colonized by you a couple of years ago. So I would like to warmly thank our friends from Salfo who have organized this meeting on behalf of the eSafe Consortium and the University of Catania. So I usually start my presentations on this topic with a question. Why renovate? Why should we renovate buildings? So maybe you know part of the answer, but I would like to give you also my part of the answer. So in the European seismic countries, most of the building stock is highly energy consuming and highly earthquake prone. Why? Because it was built before the enforcement of affecting energy and seismic regulations. As Mr. Bornas already said, we know that 50% of the Italian energy demand, buildings are responsible for 50% of the final energy demand, which is a lot. But more importantly, only in Europe and only in the last 50 years, earthquakes have caused over 36,000 deaths, around 1.3 million homeless, and around $220 billion monetary losses, which is also a lot. I would say this is enough. And these figures that you see here do not entail the earthquakes that recently struck countries close to our European borders, namely in the last February, Syria and Turkey, and Morocco in last month, causing both together nearly 60,000 deaths. So we must consider that investing in disaster preparedness before a national hazard like an earthquake occurs will considerably reduce the need for humanitarian action. And according to the estimations of the United Nations Development Programme, every dollar spent in reducing people's vulnerability to disaster like earthquakes will save around $7 in economic loss. This is a ratio of 1 to 7, which is really relevant. And this is without considering human losses, human suffering, and social harm. So this is why it is essential, in my opinion, to renovate buildings. So actually, in recent years, in the last years, important steps have been taken to improve the energy efficiency, but not as much to improve the seismic safety. And in particular, you can see here two pictures that highlight the collapse of buildings renovated only in terms of energy efficiency. On the left, one after the earthquake that struck central Italy in 2012, and on the right, one that was that collapsed in 2016. And this means that in earthquake-prone countries like Greece, like Italy, energy efficient and anti-seismic renovation intervention must be synergically combined. The problem is that the current seismic retrofit techniques, the ones which are available on the market, have relevant limits that considerably reduce the widespread diffusion. In particular, I have highlighted these main limits. We have very high costs. We have high occupants disturbance. Normally we did relocation of furniture and occupants. We have intensive and disruptive demolitions. And last but not least, long time for implementation for big apartment blocks up to 2 years. So to overcome such limits, such barriers, we have the ESAFE project. Our project is currently developing specific solutions. In particular, the main technical goal of the ESAFE project is to develop solutions which are cost-effective, low-invasive, and environmentally friendly. Such solutions are specifically devoted for the seismic energy and architectural renovation of non-historic buildings which have a reinforced concrete structure. So these solutions are not devoted for traditional masonry buildings. To this purpose, we have built a complementary multidisciplinary consortium made of 12 partners from different European countries, some of them highly earthquake-prone, like Cyprus, Turkey, Greece, and Italy. The project will last until the end of next year, more or less. So you can see here, in a nutshell, the main technological ESAFE solution to combine energy efficiency and seismic safety. It's a sort of new seismic resistant and energy efficient building scheme. So our goal is to operate mostly from the outside of the building. We have two solutions, one on the left and one on the right. The one on the left is a combination of structural panels called ECLT, the red ones, which are made of a very strong wood, the cross-laminated timber, and which are connected to existing reinforced concrete structure. And then we have non-structural panels, the yellow ones, which are mostly made of wood and insulation, and which integrate also new high-performing windows that replace the existing ones. On the right, we have the second option that entails the combination of 3D steel exoskeletons, the blue trusses that you see here, which are again connected to existing reinforced concrete frame and combined with the non-structural yellow panels, the E-panels already described before. All these components, ECLT, panel, and EXOS, are totally prefabricated. This means that we can speed up the implementation time. We can be faster and also reduce somehow also the cost and also the occupants' disturbance. So the most innovative device developed within the eSafe project is the friction damper, a device for the dissipation of the seismic energy. It is highlighted here on the right of this picture. This damper connects the existing reinforced concrete beam, this one, with the upper and lower CLT panels. In particular, as you see here, during an earthquake, the building and the damper start shaking, and the components of the damper, the upper profile and the lower profile that you see on the picture, start sliding. This sliding movement will dissipate via friction, through friction, part of the seismic energy, and this will reduce the damage suffered by the building. So this is the main idea. Both building skin solutions offer the following relevant advantages: reduce occupants' disturbance, as I said before, reduce implementation time and cost, use of bio-based materials, mostly wood, and then increase aesthetic and functional attractiveness. eSafe also integrates a new innovative technical system called eTherm that includes high-performance air-to-water heat pumps, insulated water tanks to store the thermal energy produced by the heat pumps, and then PV modules with increased self-consumption rate that will feed also the heat pumps, and fan coils fed at low-medium temperature. We have also developing specific slim tanks for the storage of domestic hot water. So, and now some possible applications of the eSafe technical concept that can be expressed in many different and customizable ways. We have 3 pilots building. One is in Italy, it's the residential building in southern Italy on the left, and then 2 pilots in Romania. So we have different climate zones to demonstrate our solution, and always seismic-prone countries. This is the first pilot building in my town in Catania in southern Italy. It is a public housing. You see on the left the current state, and then on the right a render of the post-renovation state after the application of the ECLT and ePanel solution. This render, this design has been conceived with the involvement of the residents, as my colleague will later explain better, more in detail. This is the second pilot building. It's a school building. In this case, we are going to demonstrate the eExos, the external exoskeleton solution. You see on the left the current state of the school, on the right the render of the design state already produced with the help of the students and the teachers of the school with a co-design approach. And finally, the last pilot building, which is located again in Romania, this time in Bucharest. On the left, you can see the current state of this apartment block, and on the right, a render of a possible post-renovation state after the application of the eExos and the ePanel. This is not the final solution, because we are going to design it along with the residents in the upcoming months. So in conclusion, the big hope and also the big challenge of the eSafe project is to effectively contribute to find proper solution to make our buildings and let's say also our cities more energy efficient and safer, let's say also more sustainable. To do this, we need your commitment. We need your trust, so I hope that you will offer us the chance to support, you give us the chance to support you with the eSafe solutions. Thank you very much. Questo?
Good evening, everyone. I am truly delighted to be here for this important event, where we are discussing one of the main challenges to face for the future of our city, the need to spread seismic and energy retrofitting. In the next few minutes, my task is to explore the dark side of retrofitting, that is, and I'm referring to the social aspect. There are many issues that can be raised from this perspective, but this evening I'm gonna show you what we have done in terms of co-design as a part of the SAFE project. When we say co-design, we refer to a participatory and co-creative approach where building and users directly collaborate through the entire design process with professionals, so they can together identify the best retrofit solution within a common framework. It's crucial to note that the decision to adopt a co-design approach should be made with the understanding that co-design is not an additional commitment, but is a shift in the designer conventional mindset. Such an approach prioritizes mutual learning, a mutual learning attitude, and both resident and professional learn from each other. Specifically, professionals learn from residents about their needs and preferences, while residents learn from professionals what can or should be done in terms of technical constraints and procedures. In ESAFE, as Professor Margani said, we are experienced two co-design process so far. In Catania for a public housing building, where ESAFE will be implemented, and in Timișoara for a public school. And in the next month, we will work also in Bucharest in another residential building. And now I'm going to show you in detail what we did in Catania, and I'll try to give you some highlights of the co-design in Timișoara. So, co-design is not an event, but is a complex social process, so it's expected to be as diverse as the people involved and the issues that are at stake. Consequently, we have not an applicable step-by-step procedural instruction, but however, the two processes were structured according to a general idealization of three basic sequential phases: the outreach, the co-analysis, and the co-design. So go deep in each phase. The initial outreach phase is essential because it ensures that all the people involved in the co-design process are those who can take an effective decision on seismic and energy intervention that need to be implemented. The outreach phases provide also the basis for developing a collaborative environment since the very beginning, and this is particularly true in a context like the one in Catania, characterized by a high level of distress and social vulnerability. In the case of Catania, the outreach phase started with a community meeting carried out in the courtyard of the residential complex that was attended by the resident of the building to be renovated, representative of the public housing agency, the representative of UNICT, and also representative of the local tenants union. The aim of that first meeting was to present an overview of the SAFE project, the future activity of co-design process, and to make residents aware of which interventions were covered by the budget of the SAFE project, and which were not covered should have been included in the design only if owners were willing to pay. In this phase, as facilitator and social people of the project, we also spent a huge amount of time to one-to-one meeting in order to give people clarification and to feed an environment of mutual trust. After this first phase, the second one is the co-analysis that is aimed at collecting data for the building project. The overall purpose of this phase is to embed resident relevant knowledge in the development of the energy and seismic retrofitting solution. but it's also the moment when residents and stakeholders learning about renovation opportunities and barriers. Beyond data collecting, the main objective is both for stakeholder and professional to learn about each other's perspective while recognize their reciprocal value. How we conduct this phase? We contacted residents via phone interview due to COVID restriction at that time with a protocol made of 18 questions on the state and use of thermal plants. We asked them how they cooling it and produce domestic hot water. About bill expenses, we asked also residents to send us copies of their bills. I can assure you that all has been done in compliance with the privacy policy. The presence and use of veranda, the implementation of recent renovation work, and structural and functional issue. And also we asked them about relevant problems at the complex and at neighborhood scale. This was also the phase for the preliminary survey of the building, conventional survey of the building carried out by the team of engineers and architects. Once a first collection of data was completed, we moved into the co-design phase. And the overall goal of this step is getting all the people involved in a designer thinking attitude. This implies simplify as much as possible the design process and focusing each meeting on a single topic that can be addressed collectively. So we decided to organize an intensive co-design workshop in the fall 2021. And except some studio activity reserved to UniCT student researcher, as you can see in this picture, all the meetings were scheduled over the weekend and located in the pilot courtyard, so to maximize the resident ability to participate. In the workshop, we face all the aspects of a project: structure, thermal plans, aesthetic issue, and all the detailed activities are described in a public document that is the report of engagement co-learning activity that you can find Googling on our eSafe community in Zenodo. But here I like to point out the use of some tools that help people with no experience in the field of retrofitting and building construction to be able to communicate each other. This is the case of photo voice exercise, what is photo voice? At the end of a meeting, of a workshop meeting, we ask each resident to share via WhatsApp or email a picture of their dream building. What is a dream building? An image representing a building similar to theirs, but with a much nicer appearance. Such a technique used photography as a communicative mean in the hands of residents who were not necessarily trained to think and talk about building aesthetics, which might be difficult through traditional communication channels such as speaking or writing. And I was underlining that is especially true in a context like the one in Catania with a general low level of education. So during the following meeting, we examined the result of the photo voice exercise with the residents and discussed with them potential shared preferences. The discussion led to 6 different design ideas that are a little bit small on your right. And the student researcher produced visual materials to be shared with residents and get a collective decision. The main point here is that co-design enables people to communicate each other. During the month following the workshop, UniCT experts used the outcome of the workshop to develop the final design. And in this phase, meetings with residents were more sporadic, as you can see in the table, and were structured around very specific topics that emerged while working on the project at a more detailed level. Also, in this case, I'd like to point out some issues that are relevant if we conceive the retrofitting not just a technical matter, but also a social one. This is the case of the removal of veranda. Veranda in this pilot were beloved by residents, but need to be removed urgently for 2 reasons. They were an obstacle for a detailed laser scanning of the building, and they were a legal obstacle to the submission of the application for a renovation permit to the local authorities, since only 2 out of 7 verandas were legally authorized. The discussion with residents, therefore focusing on explaining why keeping the veranda basically meant preventing deep retrofitting of the building. But also the discussion triggered a more general reflection on the need to balance the single household needs, that is keeping the veranda, with the collective interest, that is the ability to file for the renovation. At the end, residents agreed to remove the veranda under the condition to develop a final design that included the aesthetic and functional possibility to build new ones. The other issue that have an interest from a social perspective is the installation of a thermo-centralized system. Experts explain how we work the new plans and point out the pros and the cons. Of course, the new system has the advance of generate significant saving, is an innovative system from a technical point of view, but the main disadvantage was the coexistence of the new system with the current one to be used only for powering household appliances. This will mean that residents will pay 2 bills. Despite the savings that are very high, residents show significant concern about the duplication of bills. The discussion brought to the light the underlying reason beyond such a concern, which was the centralized nature of the system. And for us, this is not a surprise. For a social system made of people with limited economic means and characterized by a lack of mutual trust when it comes to paying bills. The meeting ended with an agreement that a future meeting will be dedicated exclusively to the calculation of the exact quota based on equitable distribution criteria and to the detailed simulation of the cost per household. This is, as Giuseppe showed, the final project as an outcome from the co-design. We also conduct a co-design process for a public school in Timisoara, and also in this case we organize a first moment of outreach and stakeholder mapping, and then the co-analysis was carried out through a focus group with students, teachers, the principal of the school, other public authorities in the field of education, to raise the main aspect to work on the project. And then we carry out workshop meeting where we work together with also craft activities to give an identity to the EXOS elements and take into account design elements for visual and thermal indoor quality. And I don't want to bore you any longer. And for further information on this process, you can visit our website and or text us, and we would be very happy to share with you all the things that we have done. To get the conclusion, a co-design process pushes us to conceptualize the building not just a material entity to be modified, but as a complex system where the material dimension relates to the human one. When we started the process in Catania, the atmosphere was hostile due to pre-existing conflict between both public institution and the resident, as well as among residents. And the simple experience of meeting periodically with facilitator pushing for mutual respect, listening and understanding, helping in dealing with controversial issues and reaching out to collective decisions. The frame of the 3 phases, outreach, co-analysis and co-design, follows a conceptual roadmap that facilitates a shared understanding of a participative method that gives value to the mutual learning of people involved, as well as the co-design of solution. Nevertheless, the co-design process is based on an open approach, which means tailoring the activity to the resources of the context and the stakeholders' capability, beyond the roadmap. Finally, the open and evolving nature of this process requires professionals to acquire a multidisciplinary mindset as well as relational skills. This is particularly true in the case of those projects characterized by a prominent level of complexities that go beyond the simple technical issue, as in the case of working in the stressed urban area. This implies that the role of professional that facilitates the process is central. He or she is the person who balances time, effort, but overall has a clear idea of the goals that can be reached. That's all. Thank you.
Thank you very much. Η επόμενη τοποθέτηση θα γίνει.
Now, the next presentation is by Mr. Aris Papadopoulos from ZVSA ESCO.
Ναι. Το βελάκι πάει πάνω κάτω. Ναι. Page down.
Page up, page down. Page up,
Okay.
page down.
Καλησπέρα. Καταρχήν θέλω να ευχαριστήσω την εταιρεία Σάλφο για την ευκαιρία που μας δίνει για αυτή την...
First of all, I would like to thank Salfo for the opportunity they have given us to participate in this conference. It is very important, and I confess that as I was preparing for this presentation, we were considering what we should answer to the question about energy efficiency and funding, and how they relate with seismic evaluation. At the beginning, it was said that many steps were made in the last 5 years. Many steps were taken in the last 5 years. It is important to say that there's been some projects that are trying to be completed. They have been trying for 7 years now. And I'm talking about Electra, a program which started 7 years ago and has not managed to proceed. Why? Because Electra had to deal with an issue of funding and actually third-party financing in energy-saving projects, especially through the European Investment Bank. So when we are talking about third-party financing, third-party funding, two important factors need to be taken into consideration. First of all, the performance of the measures. Energy efficiency is important. What will happen in the 10-15 years, in the next 10 or 15 years, and then the performance of the project itself. I heard the presentation about Samos. I heard you saying something about that. And I think that schools were supposed to be part of this project, Electra. If the school in Samos had been completed, not with a grant, but with Electra, with the participation of the European Investment Bank, if this had happened, what would be the fate of this school? All these years in Greece, foreign companies that have already completed many public projects abroad cannot invest and finance projects in Greece. Why? Because these constructions have a specific way of being performed, and we need to think about the near future, the next 10 and 15 years when we make them. Especially in an earthquake-prone country like Greece, which is also a country full of islands. How could we do all this when the quality of construction is what we need, especially in the next 10 years? How can they finance a project with a risk analysis for the next 10 or 15 years when other things need to be taken into consideration as well? For instance, the climate change, the level of temperatures in the near future, how we will use them in the models, and then we need to decide what kind of quality this construction should have in order to be able to resist in any issue in the next 10 or 15 years. So, we are talking about public projects which are performed through grants. This is a very usual thing in Greece, and we have a specific track to follow. But if we need to do something with third-party funding, then that's a different story. I've been trying to follow what is happening in this field in order to be able to understand if we can do something in the future in Greece. In Greece in general, there is confusion as regards what energy efficiency involves. If one wants to make a thermal insulation, for example, in order for this to be operational in terms of economic models, it is very difficult because if we take the views of people who are more specialists than I am, one of the things that we need to do is to take into consideration seismic considerations, etc. And this will make the project even more costly. Then, if the cost is higher, financing becomes even more difficult. So you understand what the fate of these projects will be. That's why I'm saying that this project is very interesting for us. We've been following it since we were informed about it. We are waiting for the conclusions because we will have to take these conclusions and try to implement them in the private sector, because the private sector is different. This is the next day. We're already there. We have to have that in mind, because energy efficiency and seismic protection needs to be combined with other certifications. For LEED, it's the well certification, for instance. The materials used for the project are important as well, because the whole approach that needs to be taken has to be holistic in order to have real energy savings and have an energy efficiency that resists in time and reduces risks. Thank you very much. Now, Mr. Dimitris Balis has the floor.
Είσαι λοιπόν. Είναι εδώ πέρα πάνω, δείξτε λίγο την παρουσίαση.
Good evening, everyone. My name is Dimitris Balis, and I'm a civil engineer. I represent CERS Group, where we have a strong experience in instrument-based investigation of existing structures and the implementation of rehabilitation works. Honestly, we are not designers. In our experience, we believe that the process of structural rehabilitation can be divided in 4 steps. The first step is the assessment of the existing construction. The second would be the determination of the importance factor and the acceptable limits of risk factors in collaboration with the owner, the employer, the end user. The third step would be the identification of the technical demands and the identification of the operational restraints as well, a step which is extremely important. And the fourth step, although significant, it is a major step. It is the step where the structural design and implementation must take place. In the first stage, we identify the type of the structure. It could be buildings such as hospitals, hotels, industrial projects, and infrastructure. The assessment must originally begin as qualitative and then quantitative. When we have the quantitative assessment, we can either use measurement-based assessment or model-based assessment. The evaluation process involves a number of laboratory and in situ tests. This can be concrete compressive strength test, concrete carbonation, reinforcement detection, chloride content, half cell potential, linear polarization resistance, ultrasonic tests, and X-ray to reach something in larger depth. We also must implement tests such as steel hardness testing, steel tensile test, and pull-off test to identify the concrete tensile strength. There are a number of regulations that can be followed in order to implement the rehabilitation. There are a number of international regulations, such as FEMA 454, where in this table below we see the comparative cross-reference of various seismic performance ratings. In this table we see how different buildings are benchmarked according to seismic design provisions. And of course, There are cases where special conditions, such as hospitals in this case, the buildings are rated for a combination of structural and non-structural performance indications. In Greece, the most relevant regulation is CANEPE. It is the regulation for structural intervention. In this table, the anticipated performance of the building is identified. CANEPE also introduces that there are different zones of seismic activity across Greece, and there are buildings which are categorized differently with reference to their importance. There are 4 different categories, as we probably all know, and they mostly are categorized in terms of their own importance. In the third phase, in the third stage, what we must do is identify the technical demands and the technical restrictions of the structure. For instance, we might see that there is a need to increase the elements' bearer strength, to increase the deformation capacity, the absorption capacity, and perhaps the seismic isolation of the building. However, there are always restrictions that must be considered. Restrictions in terms of functionality, of the way that the rehabilitation interventions will be rehabilitated, the correction of defects, the rehabilitation process that perhaps must take place either in use or not of the building, the progressive implementation of the rehabilitation, and the application, as a possibility, the application of the rehabilitation interventions only in the exterior of the building. In general, the restrictions can be summed up as restrictions in time, cost, and the impact they have on the functionality and the use of the building. During the design phase, we must also keep in mind that apart from the CANEPE, the design must also follow the principles of the relevant EN code, both for damaged concrete and for corroded reinforcement. A short description of the classic methodologies in terms of rehabilitation procedures are indicated below. It is the increase of cross-sections using shotcrete or cast in situ reinforced concrete, the use of steel jacketing, the addition of new steel elements, the addition of laminated steel strips, and the use of injection resins. More innovative methodologies of rehabilitation involve the application of FRPs, involve the epoxy mortars to use with steel strips, the use of specific steel bracings inside the buildings and outside of them, and even more innovative methodologies such as the external post-tensioning system or the application of seismic isolation systems. And we always must keep into consideration the fact that the durability issues have to be addressed as well. Corrosion inhibitors must be applied, zinc anodes for galvanic protection, where the case demands, or aluminum anodes, and even protection system for the concrete surfaces. There are advantages and disadvantages on the methodologies that are more common in the Greek market. The most common approach in the Greek market for rehabilitation process is the shotcrete approach. This approach offers certain advantages such as the small thickness of application, the high compression strength, the very good adhesion, and it is fire resistant. Quickly, we may say that it requires careful preparation, and it involves a lot of dust and a lot of noise. Here are some pictures of implementation of the short-reef methodology. The injections, the epoxy resin injections. This can assist in sealing of active or non-active cracks with different widths. And of course, this can be implemented even in the presence of moisture. However, this methodology is not applicable when the damages are serious, and it needs some fire-resistant cover. These are different pictures of application of resins in different structures, concrete structures. Cast in situ concrete. This requires less preparation of concrete surfaces. This has a lower cost of application, a lower need of expertise, and it is fire resistant. However, it requires framework, it requires formwork, and it requires a lot of space to be implemented. Different pictures of projects where in situ concrete has been applied. Cementitious polymeric mortars. The plus for them is that they can achieve quite small thicknesses, they have high adhesion, and they are a fire-resistant method. However, they have increased costs, and they have great sensitivity in the mixture process. The main problem with them is that sometimes they can easily be considered as they don't have a need for expert application, where this is actually not the case. Different pictures of this type of rehabilitation. Composite materials, something also very common here in Greece. It is a clean application, a quick application. The dimensions of the strengthened elements remain almost unchanged. FRP's mechanical properties remain unchanged in time as well. They can be painted and they can be coated. Nowadays, they have a low cost and they have a short time of application. However, they require additional measures. They require painting, they require coating in order to become fire resistant. They need careful and detailed preparation, and they are in need of expert application. These are some pictures of specific FRP projects that were implemented here in Greece and in Athens specifically. Steel bracings in general, and steel elements in general. Steel can undertake large plastic deformations. They have a low application cost, and they can used for extensive interventions to the existing structures, which are not required, which can lead to minimum interruption in the service operation as they are applied in the facade. As a disadvantage, we can say that the steel and reinforced concrete have different post-elastic behavior, and of course they are in need of coating protection for purposes of fire resistance and corrosion. In this picture, we can see not only steel bracing, but steel strips and other forms of steel elements being adopted for rehabilitation purposes. A more modern technology, a more modern method of structural intervention and rehabilitation is the external post-tensioning system. This actually leads into resetting the bending deflection of beams and slabs. It leads to sealing of cracks in order to avoid reinforcement corrosion and does not increase the total mass of the construction. It is measurable and adjustable due to the future needs and can be redesigned. However, it has large axial forces imposed on columns due to the cable anchoring. There is extreme need for design and implementation expertise, and the cost is significant. To my knowledge, this methodology in Greece has so far only been implemented in bridges, never in a building. here is a bridge where this rehabilitation process was implemented. Another very modern rehabilitation approach is the seismic isolation in existing structures. This leads to the abolition of requirements for elements plasticity. However, it has very high expertise design requirements, and it is of an increased cost. In Greece, seismic isolation has so far only been applied in new buildings. And to my knowledge, there are only 3 buildings in Athens where seismic isolation has been adopted as a solution. So far, I do not know of any building here in Greece an existing building in Greece, where the seismic isolation has been adopted as a rehabilitation methodology. However, this is something very common in our neighbor countries. It has been implemented in Turkey, in hospitals in Turkey, and it has been implemented in Italy as well. Here are some pictures of bearings and seismic isolators and dampers used in general. Given the volume of existing old buildings in Greece and the delay that has been exhibiting so far in adopting all these new approaches in the Greek market, to my mind, it is imperative to experiment and find new methodologies, such as the one we've seen, in order to create rapidly a safe and functional building environment. Thank you very much.
Thank you very much. Now, with Mr. Ballis' presentation, we have completed the round of presentations. Now we will start with the Q&A session. Please, let's start with the questions. First to Mr. Bournas. I'm Vasilis Kyriakopoulos. My question has to do with seismic upgrade and its cost. What would be the best tool to have a combined seismic and energy upgrade?
Ακούτε?
Ναι. Can you hear me?
Δεν...
Δοκιμάστε λίγο πάλι, σας παρακαλώ.
Τώρα με ακούτε?
Ναι, σας ακούω.
Can you hear me now? Well, if I understood correctly, you asked about the cost, if it is, what cost is higher, the seismic or energy efficiency, effectiveness cost? No, I spoke about the financing tool that would be appropriate for a combined upgrade. Well, it has to do with the vulnerability of the building and the proposed method. Depending on those elements, the cost can be different. What we found as a solution unfortunately, the sound is not good, and we cannot really understand what the speaker says. We will do our best. When you combine that with the energy upgrade, you can reduce cost because the same scaffolding, the same team of experts can do both. Some other solutions would be the panels, CNG panels, which are more expensive If I'm not mistaken, they are 300 to 400 euros per meter, depending on the country. So what we propose is that when a country has a renovation strategy, it has to take into consideration the seismic vulnerability of the buildings, as we had in Italy, an example. Which unfortunately stopped. It was not ideal. There was a great rise in construction and retrofitting prices. The idea was to cover 100% of cost, but due to these grants, then cost was skyrocketed in Italy.
Πιστεύω ότι υπάρχει μια ορθολογική χρήση και
if we have a rational use of the funds, it could work, but we have to find the resources from the member state that will support this program. In some cases, the cost is too high. Thank you very much. Next question. If there are no more questions to Mr. Bournas, we would like to thank him for his participation. Thank you very much. Goodbye. I would like to thank you for the invitation. I apologize for not being there with you, but I had to travel to Brussels.
Ευχαριστώ πολύ. Γεια σας.
Γεια σας.
Goodbye. Now we can start the round of questions to the rest of the speakers, of the rest of the people who made a presentation.
Στρατιάδης Δημήτρης, Ελληνική.
I'm Dimitris Stratiadis from Ελληνική Μελετητική. What are the next steps? That's the question. I don't know who wants to answer, but what is your plan for the future? And another question has to do with whether research and procedures will focus on the methods that you've just described, or whether you're open to other proposals as well.
Yes. Yes, I was.
The question was off the mic.
Whom I should address them. One of them is very interesting, obviously, for all of us. But I was wondering if the next steps have been determined for this procedure. What's the process of trying to implement these proposals? Is it in Greece or in Italy or in general? And the second one is whether the research and the implementation will be limited to these two, the exoskeleton and the ECLT, for example, proposals, or are there other proposals going to be investigated?
Okay, thank you for the question. So at this stage, we're going to demonstrate our solution. So we have done all the theoretical work, let's say, and now we are going to implement them. We have already done with part of the most of the project for the pilot in Catania, my town, in southern Italy. The problem is just now to find a company that will make the work, because as Mr. Bona said, there is a skyrocketing increase of construction costs in Italy, and so it's really difficult to find a company that will do this job with our budget. Not because it's really low, but because, I mean, it's really crazy at the moment. They just do works only when they have a very, very high profit that was not believable in the past, but now they are spoiled, let's say. So now the next step is to try to implement also our solutions in the two pilots in Romania. For these two pilots, we don't have the budget. The European Commission didn't provide a budget, but the local actors, the local stakeholders are trying to find the budget, so they are going to implement the solution with their own money, let's say. And we don't have at the moment other solutions. You say we have actually these two options for the combined seismic and energy renovation. The one which is bidimensional, let's say, just panels, structural and non-structural, and the other one that is also a new skin, but it's not bidimensional. Let's say it's three-dimensional, because you have exoskeletons, and they will entail a thickness of 3-4 meters maybe, and so you need more room around the building. You cannot put them on a private walkway, for example, so you need isolated buildings. It's okay. It's yeah.
Ευχαριστούμε πολύ. Αν δεν υπάρχει κάποια άλλη ερώτηση, μπορούμε να προχωρήσουμε στο κλείσιμο της εκδήλωσης, καθώς έχει ολοκληρωθεί και η διάρκεια που είχαμε προγραμματίσει. Καλώς. Σας ευχαριστούμε πάρα πολύ.
Thank you very much for being here today. I hope you can join us in the future as well. Thank you very much.